Okay, good afternoon. This presentation is on OCP data plane acceleration for Edge Cloud. Maybe we should go around and introduce ourselves. I was up here the last meeting or the last presentation. My name's Mike Moore. I'm the AirFrame openEDGE. Well, I got the new title of marketing director, but I guess being part of the OCP committee has a little bit of marketing involved in it. So maybe we want to go around.
Yep, and Ash Bhalgat, I'm the Senior Director for Cloud Marketing for Mellanox, and I work with Nokia and Nuage and to kind of get into the cloud ecosystem and developing the cloud market for 5G, Edge, as well as the hyperscalers.
Okay, and I'm Mark Iskra. I'm a technical marketing engineer working at Nuage Networks, developing market solutions with our partners. Nuage, by the way, is the French word for cloud, so Nuage means cloud networking.
Okay, so it might seem a little redundant for you that have been sitting around here for a while, but basically at the far edge, the key to this is minimizing latency and increasing throughput, especially as we're moving to 5G. The 5G air interface does a lot to reduce latency and increase bandwidth over 4G. The other key to reducing latency and optimizing your throughput is to actually locate those compute resources as close as needed to the end user. And so that was basically the genesis for the AirFrame openEDGE server. I've been over the specs again. Key to it is low depth, being able to fit into edge and far edge deployments, and improved environmental specifications over your typical data center environments. That includes full NEBS compliance, seismic zone 4 compliance, and extended operating temperature ranges. So the sleds themselves, we have a 1U and a 2U sled. 1U is really very much compute intensive, doesn't have a lot of I/O associated with it, not a lot of storage. If you need additional storage, additional acceleration capabilities, or additional I/O capabilities, the 2U sled will fulfill that need. And then some of the installation examples, as shown earlier, we have from the right to the left, we have a outdoor enclosure that can even be pole mounted. That is actually maybe the first 100-core pole-mounted data center deployed. And then the middle is a 600-millimeter rack, and then it's also designed to go into a standard 19-inch EIA 310 compatible rack. And so with that, I'll turn it over to Ash, who can talk a little about the technology that's enabling this demo.
All right. Okay, thanks, Mike. So essentially, as Mike said, on the edge side, you need a micro data center, which has a very smaller footprint, real estate, power cooling, and you really need an efficient infrastructure to kind of drive high throughput, lower latency. And that's where I think Mellanox is centered around the innovation on the edge. And what we are doing is with our ConnectX family of ASIC-based NICs, we enable the innovation to drive higher efficiency at the edge. We have ConnectX-5, which is it supports different speeds from 10 gig all the way up to 100 gig, and now the ConnectX-6, which is the next generation that has 200 gig dual port NIC. And it's an ASIC-based NIC, so it's not just about the speeds and feeds. It has a PCIe Gen 4 already by 16 lane NIC, so it's a really state-of-the-art, really innovative NIC in terms of the speeds and feeds. But that's not what we are really known for as Mellanox. Mellanox is known for the acceleration engines that are pre-built into this ASIC. And those acceleration engines are from anything for networking and storage, right from doing offloads for virtual switching, such as an OVS offload solution, running just a DPDK if you're running on a CPU bound software optimization, doing that even better than most of the other NICs out there. We do things such as SRIOE, NVMe or fabrics for storage, Rocky, or the VXLAN NCAP decap, or NVGRE NCAPs decap for overlay networking. So there's a lot of pre-built, purpose-built functionality that's already out there in the silicon that can be exposed for the cloud environments. So that's basically what ConnectX-5 does. It's an intelligent NIC, but I really want to call it a cloud NIC because it can be used in all cloud environment, being hyperscalers or Telco Cloud or Edge Cloud. And so one of the key technologies out there that I briefly touched upon is the virtual switch offload. And this is typically required in a high-density server, on an edge server, where you find that there are a multitude of microservices running, for example, in a container or on virtual machines. And then you want to switch the traffic between the different containers or the VMs. And how do you do that in the most effective manner without consuming a lot of CPU? And that's a technology that we have already pre-built in the ConnectX-5 silicon. It's called as ASAP squared, and it stands for accelerated switching and packet processing. And that's why the P squared at the end. But essentially what it is if you look at this diagram here, the day in the life of a packet is normally you receive a packet on the wire, and then you look at the packet in terms of the tuples on the packet. So it might be the source MAC, destination MAC, et cetera, and you have 5 tuple or 7 tuples. And then you classify those packets into different flows. And those flows, flow classification is one of the key elements of what do you do with the packet, right? And so that's the second thing on the packet that happens, which is once you match the flows, you take an action that's based on what has been pre-programmed, right, into the router or a switch. And all of this functionality can be easily done in a smart NIC or a intelligent NIC that Mellanox provides today, so that you can do this on a simple network adapter card, as opposed to consuming an expensive CPU resource to do that, right? And so as an example, if you're using OVS or Open Virtual Switch or any other vRouter for that purpose, you could easily offload the programming of the software rules or the flow programming that happens in the hypervisor in the OVS typically, that can be easily offloaded to a eSwitch of the ConnectX-5 NIC. And what it does is you can programmatically put the SDN control from the OVS or an SDN controller to insert the rules through standard interface, such as an API, such as Linux TC Flower, into the eSwitch. And then that takes care of the control plane, so it's still SDNized. But then the data plane is all SRIOV, going all the way from the eSwitch to the VMs or the virtual functions that are SRIOV VFs. So that gives you basically based off both worlds in terms of not only having a faster data path, really line rate throughputs, but also being able to program that programmatically, program the switch programmatically using standard Linux APIs like TC Flower. And if you look at it in the packet flow on the right-hand side here, you can see the first packet which comes in on the wire, like I showed in the life of a packet diagram. You would not see that packet being known to the eSwitch because there's no flow entry or the rule already inserted into the eSwitch for that. But what happens in the next packet is once you have the flow entry already programmed through the flow API, the next packet that is coming in gets hardware switched, fast switched, instead of having to go to the software, which is the OVS in this case, right? So that's really the beauty of a hardware offload solution, where you can really realize high packet rate and really line rate throughputs by doing this in a custom-built ASIC that's purpose-built for that purpose. One of the key things that comes up all the time is why not use something called as DPDK to run a virtual switch on? And that's definitely an option, and we have the best DPDK performance in the industry for our NICs. We can go up to 148 million packets per second for small packets. That's really high. But essentially what you find is that's more normal VLAN kind of packets. But what you find is even the DPDK is an on-load technology, where what you do is if you're doing overlay networking for VXLAN, it does consume a lot of CPU cores to do the encap and decap. So for example, in this case on the chart as it shows here, you can run OVS over DPDK, and with just 2 cores, you can get 7.6 million packets per second. And that's a pretty good number if you were kind of running it and willing to offer and consume a lot more cores for that. But as you grow up the throughput, let's say to 66 million packets per second, this number will almost go to 20 or 30 cores. And that's almost wiping out the entire sled, right, for that purpose. So if you look at it on the OVS offload technology, you don't use, because you're offloading this all to the eSwitch and not doing the software-based processing in the CPU, you can completely offload this into this functionality of the packet processing and encapsulation, decapsulation into the eSwitch with 0 CPU consumption. That's really the beauty of it. You don't have any more CPU consumed. You save all of your CapEx spending that you're spending on your cores, and freeing it up in a fraction of the cost that a NIC would cost you to do that, right? So it's really a great ROI for your infrastructure. And that's really the beauty. You can go up to 66 million packets a second. Mark will talk about some numbers that he measured in the whole demo that he did. But essentially, we have this solution is not a locked solution. It's not a vendor locked solution. All of the TC Flower kind of APIs are Linux standard APIs, and Mellanox has really done a lot of work in the community to enable upstream all of this code. We are fully supported in all of the standard Linux distributions. There's no patches to do for this kind of work. It's all in box in standard Linux distribution and in standard OpenStack kind of orchestration cloud management platforms. And it's all well ecosystem integrated, such as with Nuage Networks and other vendors. So with that, I just want to hand it over to Mark to talk about the demo and how the SDN controller brings the overall automation and management of this obvious offload feature. Go ahead, Mark.
So let's take a step back and just take a look at the bigger Telco Cloud picture for a second. Really, the purpose of this talk is to show how the openEDGE solutions being put together by OCP, for instance, fit together to create something that's useful. And what we want to do is provide some kind of indication of what's possible with these solutions today with the current state of the art. This is really not intended to be a product pitch, but you have to pick something to work from. And so, we're working with the components we have, and the end game here is really just to try to show what the possibilities are. And as Ash mentioned, all of this stuff is built up around open APIs, so you can plug things in and put different stuff in and build stuff and compose things the way you like. So in the Telco Cloud, you have a wide range of different management systems that are controlling both VNFs and also CNFs, containerized virtual functions. And there are different management systems that do that. You have OpenStack, you have ESX VMware, you have Kubernetes, and others. So there's a kind of a Wild West out there in terms of all the different things that are controlling things. Then there needs to be some kind of network infrastructure that laces all that together. And that's basically what software-defined networking does. In this case, we're showing the Nuage Networks software-defined networking. Nuage is a part of Nokia, by the way. So we have 3 layers, essentially, in our architecture. The top layer is what we call the services directory. This is really management. This is where all the rules get established for how you want things to behave when containers get instantiated, when new guys show up in the network, when you want different policies enforced, if you want rate limiting. All these things become rule-based, and those rules are contained in the management layer. Then the management rules are implemented by an SDN controller. In our case, we just call it the Virtualized Services Controller. And the Virtualized Services Controller talks to compute nodes which are running Open vSwitch. So our Open vSwitch implementation leverages the TC Flower API to talk to intelligent NICs, which have a switch embedded inside of them. So this is another kind of radical change that's beginning to take shape and mature in the marketplace. The concept of having a hardware-based switch rather than a software-based switch resident right down on each individual compute node. This results in a possibility of achieving like 3 orders of magnitude difference in terms of the performance you can achieve relative to like the conventional VirtIO kernel-based flow processing that has sort of been the standard workhorse, for a lot of OpenStack and original virtualization solutions. So, it opens tremendous new vistas in terms of performance, and we'll show a little bit of that here. And again, we can bring together all kinds of different workloads in a unified networking architecture here. I should also mention that, in the context of 5G especially, the Telco Cloud has requirements even on the edge for extremely high bandwidths and for microsegmentation and multi-tenancy. This is driven largely by the fact that we're introducing EHF frequency type interfaces, antennas, which will be MIMO, so you'll have multiple inputs and outputs. Those will be shared between multiple tenants. And you'll have extremely high bandwidths because of the frequency of the antenna itself. As a result of that, you really have to have fairly high performance, and you need to be prepared to deal with that, and you need to be prepared to deal with it in the context of a very small space. And so having this high performance switch built into the NIC itself opens the door for being able to meet those requirements. So one of the biggest challenges in deploying any kind of virtualized telco cloud solution is not so much getting VMs to launch or getting storage attached, but it's really around getting the right networking set up. And very typically, there's a lot of factors that have to go into the network design. It's defining what VLANs will be attached to different VMs, what the ACLs will be, what's the stitching to the wide area network, what is the route discovery mechanism. All that stuff, if it's done manually, can be extremely time consuming. I mean, measured in times of days, even months. Whereas, you can launch a VM and allocate resources with something like VMware or OpenStack in just a matter of seconds. So to address that problem, we need SDN, which has the ability to implement all these rules and to make these kind of decisions automatically based on a request. So what Nuage has done has basically put an integration into the cloud management software systems, things like OpenStack, for instance, or Kubernetes, which allow you to launch all these resources and then also implement the correct cloud policies and then network policies. And then we've taken it a step further and also added the ability to support a TC Flower interface and an accelerated data plane. And so when you put all that together and you start to look at how like VXLAN performance behaves in this environment, we can see what the performance looks like. And so this chart here is some data that I collected quite a while ago. This was actually done about 8 months ago using a 100 gig Mellanox ConnectX-5 NIC using RHEL 7.5 as the host and the guest. And just using DPDK apps like T-Rex and TestPMD to generate traffic loads and send data back and forth between a pair of hypervisors through a VXLAN tunnel. VXLAN tunnels in some sense are synonymous with microsegmentation. You basically allow users to have free reign over the IP address spaces that they use. They are encapsulated into a VXLAN tunnel, and then they're shot out through the network. So that's really great because everybody can kind of have their own networks. You can have overlapping address spaces, but you also bring in a lot of extra overhead by putting those encapsulations into place. And so being able to push all that encapsulation work off of the CPU and down into the NIC and the switch on the NIC makes a tremendous difference. And so, for instance, for 64-byte frames, if you were like doing real small messaging, for instance, you might have small frames. What we measured was around 56 million packets per second unidirectionally. So, if you think about it bidirectionally, then that's, well over 100 million packets per second, which is an insanely fast throughput or a very high number of packets to process. Forgive me. And you can also see that this is well above 25 gigs per second. So what this means is that you can pretty much run at line rate no matter what your packet sizes are, in this kind of scenario. So it's optimal utilization of the resources you have. So again, just to underscore the fact that all of this is built on open standards, the environment for doing this testing is basically a kernel that's maybe 4.8 or later in terms of Linux kernels. A lot of that had been backported by Red Hat, for instance, into the RHEL 7.5 release. And then OVS carries the TC Flower interface to the NIC, and from 2.8 on, OVS has supported this. And then OpenStack Queens provides the integration required to actually deploy this if you want to use an OpenStack type environment. And then commercially, you know, the Nuage VSP 5.41 release, which has just come out now, is the first commercial version that actually supports this. So a lot of this work was originally done just through early implementations and, you know, while we were in the testing process. Again, RHEL 7.5, OSP 13, and ConnectX-5 from Mellanox. So if any of this is of interest to you, you know, or you want to know more about Edge, we've provided a few URLs for you here. Also, for the hour or so that the exhibits are still open, we'll be hanging around over there at either the Nokia or Mellanox booths. So feel free to drop by to see us or catch us in the hallway. So I hope this was interesting. Any questions? We're a couple minutes over, so I guess we'll just go ahead and stop. Thanks, everybody.
Okay, thank you.